Should be up.
Show an animation here. Let's see. Ah, here it is. All right, let's see.
That's what I see too. Just a little bit of lag, but all right.
Yeah, it's like a 30-second lag.
Should we ask Ian if he can hear us?
Now they're ready.
Ian, can you hear us?
Yep.
He said something, but I couldn't hear him.
Hello? Yeah. Go ahead and begin.
Okay. All right, guys.
We got a
Well,
thumbs up from me.
we got thumbs up. All right. Well, thank you for tuning into the Launch and Learn. This week it's on 3D printing, also known as additive manufacturing by people in the industry. So in recent years, 3D printing has become more and more popular, both by hobbyists and also industry professionals and companies. Its primary use has been creating new designs and visualizing them, as well as using it to rapid prototype new parts before they're put into production. On the right side of the slide here, you can see, like I said, 25% of the reasons companies use 3D printing is for prototyping, and the rest are along the same lines of product development and just creating new things fast, quick, and cheap for their company. On this slide, there's a breakdown of the industries that use 3D printing regularly. On the top is motor vehicles, the automotive industry, which is 31.7%. This statistic, I believe, is from 2015. So since then, it has probably changed somewhat. If I had to guess, aerospace and medical would be much more towards the top, with the integration of it into prosthetics and airplanes and even the space industry. So there's 5 main types of 3D printing. We're only going to go through the top 3 on this slide, which are fused deposition modeling, stereolithography, and digital light processing. 90% of the time when someone says 3D printing, it'll be one of these 3, specifically FDM, because it's the cheapest. And when you think of 3D printing, you think of FDM. So FDM printing is extruding a piece of melted plastic onto a print bed and slowly building up a layer by layer at a time. This was one of the first types of 3D printing, and MakerBot was the company that really brought this to light and brought it from the world of companies and industries to people's houses. And it was the first time people were able to buy this technology and use it in their homes. Accuracy on this is 100 microns or 0.1 millimeters. That basically means the minimum layer height you can have is a 0.1 millimeter. Most of the time printing, you use a 0.2 millimeter layer height. So the second type is SLA, or stereolithography. It uses a laser and a moving mirror to shine the light onto the bottom of a clear build surface that's submerged in resin. And when the laser light hits the resin, it hardens and it builds the layer up layer by layer that way. These parts are very high definition and incredibly strong. They're as strong, if not stronger, than an injection molded plastic part. And the accuracy with this type is 25 microns, which is 0.025 millimeter layer height. It's practically invisible when you see it. It looks like an injection molded part. The last type is DLP, or digital light processing. This uses a UV projector, kind of like SLA, where it shines it onto the bottom of a clear print surface that's submerged in resin. When the light hits the resin, it hardens and the print surface slowly moves up and basically pulls the object out of the resin. It is a little bit less accurate than SLA. However, it is much faster, and the accuracy really depends on the projector you have. So very expensive commercial printers will have very expensive projectors which have a lot of accuracy, whereas if you buy a cheap desktop DLP printer, you might not have the same accuracy, but it'll still be much better than FDM printing. On this slide, I have a print quality comparison between FDM on the left and then SLA and DLP on the right. With FDM, you can see the characteristic layer lines of plastic, and then you can even see lumps and other imperfections that's caused by the nozzle moving around or other various setting issues. In the middle, there's SLA, where you can see the practically invisible layer lines. And then DLP is on the far right, which is has a little bit more distinguished layers, but it's still much better than the FDM prints. So since FDM is the most common type and the type that everyone associates with 3D printing, that's what we're going to talk about the most during this presentation. There are two main types of FDM printers, Cartesian and Delta printers. Cartesian use an XYZ straight axis, and it moves the print bed and extruder accordingly. These are by far the most common, and a majority of the kit printers you see, such as the Prusa, are all Cartesian because they're very simplistic and easy to assemble, and the settings are much more understandable than Delta printers. Their build volume is usually a square, and they can have much larger build volumes. However, they can't go as tall as Delta printers can. Delta printers usually print in a cylinder and much taller. However, the settings on them can be a nightmare, but when they are properly configured, they can have as good, if not better, print quality than Cartesian printers, and they can print much faster. So before we get any further, let's take a minute to talk about the file type that a majority of 3D printing softwares use, which is the STL file. STL is short for stereolithography, and it is essentially a model that is broken up into many little triangles. And this is used because it decreases the file size while keeping the surface geometry and textures of the model, as well as it is easier for the slicing software to slice it into layers and then print it. So there are a lot of different slicing softwares out there. Some of them are proprietary to a certain brand of printer. Other ones are open source. They all have their unique attributes, and a lot of different people like them for different reasons. In our lab, for our printer, I believe we're going to be using Repetier, which is a free software. It is relatively simple, but it also gives you enough options that you can fix problems in your prints, and you can customize the G-code to print it however you would like. So I'm going to pull up Repetier and do a example of how you would slice a file. So once you come into here, you can see you have the 3D viewer, which is this square would be your print bed. And then you can add a 3D object. So for this, you would either import your design that you just built in a CAD program, or you could go to a website such as Thingiverse or any other site where you can find 3D models. Another example is McMaster-Carr, where you can find any file ever for any fastener or pretty much anything. So this is Thingiverse. It's kind of like a social media platform for 3D printing. We're going to download this boat design. And then slice it. So we're back into the slicing software. And we can open up that boat. So once you have the file placed onto the print bed, it should look just like it looked in the CAD program. If it doesn't, then you have to go back and fix it, or go through manually and fix the STL file, which takes a lot of time, but sometimes it's required. And then you can go over to the slicer tab, and we're going to slice with the Cure engine. This software offers two options. You can slice with the Cure engine or slice with a program called Slicer, and each one gives you different results. It depends on your printer which one works better, but we're just going to use Cure for this. And then through here you can change the print settings, and if you go into configuration, you have even more print settings. As I'll say further on in the presentation, 3D printing is 90% or 10% hardware and 90% settings. If you have your settings right, you can get just as good a quality with a cheap printer as you can a good printer with bad settings. Once your model's in and you are happy with it, you can slice, and it will give you a little progress bar, and then it will supply you with a sliced view of your model, and then the print time, layer count, total lines, the amount of filament it will need. You can actually customize it to also tell you the price of filament based on how much you pay for the filament. There's a couple different views. This is the complete model. We can have it show a single layer. So as you drag it up, it will show us each layer all the way up to the very top, or show a layer range. So this will show it as you build it, and you can watch it build itself up just like the printer will do. Once you've done that, you can either save it to an SD card and put the SD card into your printer and print via that, or you can press the print button, and if you have a printer connected to the program, it will go straight to the printer and begin printing it. The next tab over, if we had a printer connected, you can manually control the printer, so you can unload the filament or load new filament. You can change how hot the printer is. You can change whether the fan's on or not. You can speed up the print, slow down the print, make it extrude more plastic, make it extrude less plastic. Pretty much anything you want, it can do. So yeah, that is Repetier, which is a slicing program we will be using. So like I said earlier, 3D printing is 90% about the settings. On the right here, I have 6 of the main settings which affect print quality, which are layer height, infill, speed, nozzle temperature, bed temperature, and retraction. Layer height is just what it sounds like. It's how high, how tall each layer is. From left to right here, the layers are getting smaller and smaller, and the print quality is finer and finer. It appears that the printer that printed these parts was not the best printer because there's multiple bumps and over extrusions on the print. However, you can still see that the layer height gets smaller and smaller. And as you do that, the print gets better and better quality, and the strength increases as well. But it also comes at the cost of it takes longer to print. So on the left here, printing at 0.4 millimeter layer height, it only took 15 minutes. Whereas if you go to 0.1 millimeter layer height, it takes almost an hour to print a small gear. Infill is the next setting. Infill mostly relates to how strong the print is and how much plastic you use. The higher the infill, the stronger the part will be, but the more plastic you use, which makes it for a more expensive print, and it will also take longer. There's a lot of different designs of infill. Down here, there's rectilinear, which is basically a bunch of squares. There's concentric, honeycomb. Some softwares allow you to print triangle infill, which is much stronger than square infill. So depending on the print and your printer's abilities, you should choose the right infill accordingly. The third setting is speed. As speed increases, quality decreases as a rule of thumb. That's just because you have an extruder that is moving around on an axis, and the faster it moves, the less precise it can be. Moving left to right here, it shows that going from 10 millimeters per second to 120 millimeters per second, you start getting these striations and bumps throughout the print, which if you're printing an owl like this, it might not make a big difference. However, if you're printing a moving part or something that has tolerances in it, such as a mechanical part, they will be off and the part may not work. The next is temperature. Temperature is mostly dependent on what type of filament you're printing with. PLA is by far the most common filament. It's a low temperature plastic, which is more brittle than a plastic like ABS, but it is plenty strong for a majority of applications, and it is very fast and easy to print with. It also does not shrink, and it does not tend to warp as much as a plastic like ABS does. They also have started to make specialty filaments, which have carbon fiber or wood or even ceramic infused into them, which can give your print a pretty cool feel. Or if you print with something like wood, you can sand it and it will sand like wood does. The carbon fiber prints are very light, and it doesn't offer you much of a strength benefit, but it does make it much lighter, and it's cool to say that's carbon fiber in it. Also, flexible filament has made a huge surge into the industry recently. It offers printers a whole new sector to evolve into, whereas things used to just have to be rigid parts, but now you can print it and then bend it, and it's made a whole new world of possibilities possible for 3D printers. Retraction is, I believe, the last setting we're going to talk about. This is essentially the print head pulling the filament back up through the spool, or reversing it up the extruder while it travels between objects. So that prevents it from dripping or extruding a small amount of plastic between objects. So the top here, you can see that when it was printing this, as it traveled between the two squares, some of that plastic that was left on the extruder dripped off and created this protrusion from the plastic. But moving down to the bottom, when you turn on retraction, it sucks that plastic back up and doesn't allow any to drip between. This gives you much cleaner prints and a lot less post-print work. A large part of 3D printing, a very important aspect of it, is when you're designing something for 3D printing, you have to keep that in mind while you're designing it. There's a couple things you have to watch out for. The first one is bridging. This is essentially saying that you can't print onto nothing. 3D printing is all about putting a layer on top of a layer. So when you print onto air, it just sags in between the two posts. So down at the bottom here, you can see that when they're close enough, it can bridge pretty well. However, when you get up to the top and it starts trying to bridge a piece of plastic all the way across here, it starts to sag and droop in the middle. This isn't a big deal for some prints, but again, if you're printing something with tolerances or exact measurements that's going to have other pieces that interact with it, it may not work in the end. Or you might have to do a whole bunch of post work with a file or whatever. Overhangs, kind of like the last example of bridging, you can't print onto nothing. So if you have a small overhang like this, the printer can usually deal with it, especially if it has active cooling on the print head. But once you start getting into bigger and bigger print or overhangs, the plastic starts to droop more and more, and you have to build up all this plastic before you can print the good layers up top. The second is support material. Support material is used to stop that drooping on overhangs and bridging. However, it can mess up your surface of the print if your settings are wrong, or if your design has a very intricate texture, such as this bear. The support material would probably interfere with this texture finish, and you'd have to go in with a piece of sandpaper or some sort of abrasive tool to get rid of the marks it left. Another thing to keep in mind is that when you're printing, you need to have something flat to put onto the print bed, or else you need to use a lot of support material. So in this bottom print, they have a flat surface right here, which will stick to the print bed and keep the print anchored to the print bed while it's printing. So tolerances and shrinkage. Tolerances depend mostly on what printer you have. The higher quality of printer, in general, the more precise it will be, and the less tolerance is you'll have to build into your design. However, if you're using materials like ABS or some other types of filament, you'll have to allow for shrinkage, which is essentially the plastic, when it cools down, it becomes smaller. And with something like ABS, it can be up to 0.9%, which doesn't sound like a lot, but when you are trying to design a piece that moves and is accurate to a couple thousandths, 0.9% can really throw off the entire model. The last thing is you kind of just have to be realistic. Printing can do a lot more things than a injection molding process can do. However, it's not perfect. It has its limitations, and you have to know what your printer can do and know how to either circumnavigate those challenges and print it in multiple pieces, or just work around the design complications before you print it, rather than printing something and then when it doesn't turn out, blaming the printer. If that makes sense. So the future of 3D printing, in my eyes, it's going to become a bigger and bigger player in industry because of how cheap it is and how many the technology just keeps evolving with new filaments and new, better accuracy, new types of printing. On the right, there's a chart here that showed what companies wanted to see 3D printing expand into. A really big evolution that will happen in the near future, if I had to guess, is metal 3D printing. It's already a thing. However, it's incredibly expensive and very slow. But I think the more that people innovate and work with the idea, the cheaper and better it will become, and the more and more feasible it will become. Next is flexible filaments, HTP, which is high temperature plastic. That is becoming also a more and more common thing. They now sell a filament called HTPLA, which is a high temperature PLA plastic, which you can print, and then you put it into your oven and it crystallizes the plastic, and then it can then take higher temperature and it is stronger. And then you've got carbon fiber. And then last, which I'm actually surprised at, is conductive field or circuitry. They've started to make conductive and also magnetic filaments, which people have used to print circuit boards and magnets to some extent, and a lot of other things, which could be huge. However, the conductiveness of the materials is a limiting factor. But I think with enough innovation and research and such, it could be a huge player in the industry. Right here I have some examples of some new kind of sort of cutting edge evolutions in 3D printing. It was in the news not too long ago. They've begun, a company starting to 3D print houses out of concrete. They're very heavy because they're all concrete, but it's a good step in the right direction. On the top here is 3D printed chocolate. Some restaurants and very high-end restaurants have began advertising that, and it's kind of a marketing gimmick, but you can make some pretty cool designs, and who knows, 3D printing could play a major role in the kitchen someday. And then at the bottom, there is a cellular 3D printer. Biologists and the like it's becoming more and more common for them to use 3D printers in the lab, and also 3D printing technology to print cells and to a whole scat of other processes with the cells. On the right here is just a crazy print that was done by someone. Any questions? I don't think he's in it anymore. Chris, any questions? Any questions?
How expensive is a 3D printer?
They're really cheap.
Depends on which one you get.
Yeah.
Hey, what's like the average kit versus buy it?
What do you mean, like kit versus not kit?
Yeah.
Is actually the typical 210 by 210 by 210 millimeter print bed printers have kind of averaged around $200. Some kits are cheaper, they're like 150. Some are a little bit more expensive. But I think the average, you can get an assembled 210 print bed printer for $200. Once you start getting into the bigger print sizes, like 300 or 400 or even 500, you start getting up into the $500 range. And then if you want an enclosure for printing plastics like PLA, or if you want dual print heads, because you can print dissolvable support material. So it'll print two different types of plastic, and they like submerge in like a acetone or like some sort of solvent, and it dissolves away the support material. You have to do a lot less filing and stuff like that. Those get up into the $1,000 to $5,000 range, and then above that, you start getting into commercial, which is just outrageously expensive.
$50,000.
Or more.
Or more.
Concrete printer.
Yeah, concrete printers, all sorts, chocolate printers.
Metal printers.
Yeah, metal printers.
Those.
Metal printers are like $500,000.
That's. I think that's a lot.
That's for like
I don't think
But-
those.
There's a,
what's that?
I think the 19 make them.
That's pretty cool. I'm not saying that. Yeah, I bet. That's pretty cool.
It takes a lot of that.
Pretty much. But yeah. So that's all I have. Does anyone else have any other
What's the
questions?
average cost of the materials?
A spool of filament is about 20. Well, I say $20. You can really find it for anywhere between $13 to $25 in that range. Quality varies depending on the price.
PLA.
Yeah, it's PLA. ABS is about the same price. Usually it's over $20 for ABS. But yeah, there's 330 yards on a spool of filament. 330 meters on a spool of filament. Seems surprising based on how small they are. But
How
They
much
do.
volume does it actually print out? Yeah.
that depends on the info. Yeah. So to print this boat thing that I sliced, it will take 3 meters of filament.
Wow.
So actually 4 meters of filament, really. So
Did you put
that's a good way.
diameter into that, or is it just kind of useful?
It's a 0.2 millimeter nozzle or layer height. So if you do what 4 divided by 330 times 9, it cost you 24 cents to build that boat.
What are
So-
some practical applications for like normal people for this stuff?
It depends on what you're interested in. If you, well, there's the thing that everyone says where you can print something around the house, which I've done. It's definitely useful there. Like my grill at home has 3D printed handles on it.
Very practical.
There's also tons. There's like a million different gizmos and gadgets you can print and stuff like that. But yeah, it really depends. You can really print anything. Something I think it's very beneficial for learning new CAD programs because it gives you incentive to design something. Just going into a CAD program and designing something is no fun. But if you can make it and then print it, it gives you incentive and it helps you learn a lot faster. And I think that's beneficial.
Can you talk about what you did for your piece this last year?
Yeah, I designed a lot of stuff and printed a lot of stuff. Antenna holders,
Camera holders.
camera holders,
3D sensors.
a large HAB tracker,
Yeah.
also called HAB Tracker 1. Yeah, I mean that's the beauty of 3D printing is there's really no limit to what you can do. Whatever you can design, you can make essentially. But yeah,
Very good.
well, thank you. Any other questions on the call? Yep, there's no one there.